Right, to pick up where we left off in part A, the one other thing I wanted to go over under concentration was the idea of molality. This is not in the book, so I may ask you simple questions on it on a quiz or a test, but nothing in depth. Presumably the book covers it eventually. I don't know why they wouldn't mention it here though, because it is a unit of concentration. So I thought I might better introduce it now, and then maybe we can cover it in a little more detail later. Molality is very similar in name and very similar in concept to molarity, but it is not the same. So it's molality, not molarity. And the symbol for it is a lowercase m instead of a capital M. When writing by hand, I tend to kind of exaggerate the fact that I'm talking about a lowercase m in, when it's printed or typed up. It's much easier to tell the difference. So lowercase m, molality, is often used because, again, unlike molarity, this concentration deals with the number of moles in a solution, and it makes it easy to calculate the number of moles in solution, but it's not affected by temperature. Okay. And, like I said, if you're dealing with a situation in which the temperature is changing and you don't want the concentration to change, then you need to use something like molality rather than molarity. Molality is the number of moles of solute divided by the number of kilograms of solvent. Solvent, not solution, solvent. And so that's the big difference here. Instead of volume of the entire solution, it's the mass of the entire solution in kilograms. Or sorry, see, I'm even screwing it up. The mass of the solvent alone in kilograms. Because it's a three-term equation, you can set up a little pyramid for it, where we have molality is equal to the number of moles of solute divided by the number of kilograms of solvent. You just kind of have to remember that part if you're going to use the triangle, because there's not enough room to fit all that stuff in there. But anyway, a simple, straightforward situation would be I dissolve so many grams of this stuff in this volume of water, say, what's the molality? And so here's a question like that. If you dissolve 27 grams of sodium chloride in 120 milliliters of water, what is the molality of the resulting saltwater solution? So the two things you're going to need will be the moles of the solute, that's the sodium chloride, and you're going to need the mass of the water in kilograms. Okay, so we know moles of sodium chloride you can get by taking the mass divided by the molar mass, and or multiplied by 1 over the molar mass. So we have 27 kilograms or 27 grams of NaCl times the fact that there's 1 mole of NaCl for every 58.5 grams of NaCl. That means grams of NaCl will cancel, and we get moles of NaCl, and it's 0.4615 moles of NaCl. So that's our numerator. For the denominator, we know the volume of the water is 120 milliliters, but how on earth do you get kilograms from that? Well, the one, as I said when we first talked about density, the one density of all of the substances around us that I expect you to remember is the density of water. And that's because the density of water was part of the whole setup of the metric system. It's 1 gram per milliliter, and that should be easy enough to remember. So if you've got 120 milliliters of water, that's 120 grams of water. And 120 grams of water can be converted to kilograms by dividing by 1,000. And so 120 grams of water is 0.120 kilograms of water, and that's our denominator. So the molality is 0.4615 moles of NaCl over 0.120 kilograms of water, and we end up with 3.85 3.85 followed by a lowercase m, which would be called 3.85 molal solution. All right, that was pretty straightforward. This equation, like the equation for molarity, can be rearranged. If you know the molality, you can find moles of solute or kilograms of solvent just by rearranging the equation. So for example, if you want to make a 0.15 molar solution of calcium chloride using 500 milliliters of water, what mass of calcium chloride would be required? Fair enough. So if molality is number of moles of solute divided by kilograms of solvent, then you can rearrange this equation. Moles of solute would be molality times kilograms of solvent. Okay, that's nice. So let's see, number of moles of solute. So what we need is the molarity, or molality of the solution. And then we can find the number of moles of solute in that solution. All right, so to find the number of moles of solute, we need molality of the solution times kilograms of solvent. But before we can do that, we've got the molality of solution, and we've got the kilograms of solvent we get from the milliliters of H2O. And 500 milliliters of water would be 500 grams of water. And 500 grams divided by 1,000 is 0.5 kilograms of water. So 0.15 molal times 0.5 kilograms of water would be the same actually as this. And I did this extra step here because I think that it's often clearer to see what's going on and to make sure that you're doing things correctly. Whenever you're dealing with either molarity or molality, if you write it out explicitly, what that molarity or molality means. So in this case, 0.15 lowercase m, or 0.15 molal, means 0.15 moles of CaCl2 for every 1 kilogram of H2O. And that's why multiplying this by the kilograms of H2O will give you moles of calcium chloride. Okay, so kilograms of water will end up canceling out. And it ends up that we need 0.075 moles of calcium chloride. Then we can find the mass. So whenever you're talking about molarity or molality, and also talking about mass of something, you know right away that you're going to have to go by way of moles, because molarity and molality deal with moles. If you want mass, you first have to find the number of moles, then you can multiply by, or divide, as the case may be, whatever you need to do, by the molar mass of the substance from the periodic table. So we can find the mass of CaCl2 by taking the number of moles of CaCl2 and multiplying by the molar mass, which is 111 grams of CaCl2 for every 1 mole of CaCl2. And you can see that moles of CaCl2 will cancel out, and we get grams of CaCl2 as our unit, and the number is 8.33 grams of CaCl2. And the 111 grams per mole for CaCl2, that comes from the periodic table. Again, if you add up the molar mass of 1 calcium and 2 chlorines, that totals up to 111. All right, one more. If you need to make a 1.38 molar solution of sodium nitrate while using 175 grams of sodium nitrate, how much water, in terms of volume, should you add to the solution, to the solid sodium nitrate? Okay, so in this case, we are looking at the triangle here, and basically the water would be the solvent, and the only thing that we have in the molality equation that corresponds to the solvent would be the kilograms of solvent. But of course we know the density of water, So if we can find kilograms of water required, we can change that to grams, and then we can find the number of milliliters required. So if we're solving for this, that's going to be number of moles divided by molality. Oh, okay, I already did that over here. So if molality is the number of moles of solute divided by the number of kilograms of solvent, then the number of kilograms of solvent, rearranging the equation, will be number of moles of solute divided by molality. Okay, so number of moles of solute, that's something we need. We are using 175 grams. That didn't come out too clearly, but that's 175 grams of NaNO3. And each mole of NaNO3 has a mass of 85 grams. That's from the periodic table. The atomic mass of Na is 23, nitrogen is 14, plus 3 times 16 for the oxygens, totals up to 85. And we want to divide by that because that will mean that grams of NaNO3 will cancel, and we get moles of NaNO3 as the unit for our answer. And when you take 175 divided by 85, you get 2.059 moles of NaNO3 that are required for the solution. Now you can find the mass of the water by plugging that number of moles of solute into the equation. So 2.059 moles of NaNO3 divided by 1.38 molal is the same as saying 2.059 moles of NaNO3 times dividing by 1.38 molal is the same as taking the molality and turning it upside down. So the molality is 1.38 moles of NaNO3 per kilogram of water. Turning that upside down means we're multiplying by 1 kilogram of water over 1.38 moles of NaNO3. We want the water to be on top because that's what we're looking for, and we want moles of NaNO3 to cancel. And that's what happens when you divide number of moles by molality. So you don't actually have to write it like this. I was just writing it like this to show that it definitely works. You can do it like this and it'll work out the same way. Anyway, the number of kilograms of water required will be 1.49 kilograms of water that are needed. You can then convert kilograms to grams and use the density of water to find the volume of the water. 1.49 kilograms of water times 1,000 is 1,490 grams of water, and that's the same as 1,490 milliliters of water. Of course, technically in the question I asked for the volume of water, I didn't specify milliliters. And the fact that water has a density of 1 gram per milliliter means that it also has a density of 1 kilogram per liter. Because in going from grams per milliliter to kilograms per liter, you're essentially multiplying the numerator and the denominator by 1,000 each. And so you're multiplying it by 1,000 over 1,000, which is 1. So the number comes out to be the same. So we could have gone straight from 1.49 kilograms of water to 1.49 liters of water. And we could have left it that way because liters is a volume, and I didn't specify what units I wanted for the volume. But this would be the more familiar way. If you're actually measuring it out in the lab, you're going to be measuring it out in milliliters. So you'd probably want it to be milliliters. All right, that is the end of chapter 3. Since we've actually already gotten through chapter 3, it is high time that we should be having our first basically exam for the class. And I will probably be posting that toward the end of this week, probably Thursday or Friday. And then it would be due early next week, probably Monday or Tuesday. The test, once it comes, will only include chapters 1 and 2. I know we just finished 3, but chapters 1 and 2 would be on the test. I don't want it to include too much because you've never taken a test written by me before, and so I don't want to make it worth or I don't want to inundate you with too much material all at once for the first test. So we'll say first exam on chapters 1 and 2 will come probably on Thursday or Friday. I'll post it online. I'll send out a notice by email too that it's coming. And then chapter 3 will be on the second exam, which will be sometime. Okay, since we've still got time in this segment of the video lecture, I'll take this opportunity to move on to chapter 4. Since we've finished chapter 3, that means that the homework questions for chapter 3 will be due, but I'm going to make that due next Wednesday. And next Wednesday would be so that you don't have to work on that as the same time you're working on the test. And next Wednesday would be the 10th, March 10th. And I'll announce this also through an email. And that way should keep it out of the way of the test. Okay, starting chapter 4. I haven't got the homework problems picked out for chapter 4 yet, but I'll have that soon. I'm sure you're in no hurry. Chapter 4 is some important stuff, some of which we've already done, so that should help make it a little easier. Although we're going to go into even the stuff we've already done, we're going to go into it in a little more depth in this chapter. It is about stoichiometry of chemical reactions. And stoichiometry is just a fancy word for the ratios of one thing to another in a chemical reaction. Specifically, it's using mole ratios or the coefficients in balanced chemical reactions in order to relate the quantity of one substance to another in a reaction. So, for instance, if we want to produce this much product, how much of the reactants do we need to put in? It's not going to be the same amount in most cases because we usually measure reactants and products by mass, and different compounds have different masses. So you may have to put in a small amount of reactant to get out a lot of product, or vice versa, depending on what other products are formed and that kind of thing. Or say, if you've got a certain amount of one reactant, you've only got a limited amount of that one reactant. How much of the other reactant would you need to react with it? That kind of thing. Or if you get a certain amount of this product from the reaction, how much of the other product would you also get if there's more than one product? And so this is a very useful tool when dealing with chemical reactions, whether on a small scale like in the laboratory or in a large scale like in industry where you're making tons of stuff. So you have to be able to know, to be able to predict how much of one thing will lead to how much of another thing, because there could be tons and tons of reactants or products at stake and millions of dollars too. Anyway, the equations for the chemical reactions have to be balanced in order to conform to the law of conservation of matter, or conservation of mass, whichever one you want to call it. It's essentially the same thing. That means, in effect, that you need to make sure that you have the same number of the atoms of the same elements coming out as you had going in. And that's because the law of conservation of matter says that you can't create atoms out of nowhere. Atoms can't just disappear into thin air, and you can't change one element into another through a chemical reaction. And so if you've got 3 atoms of carbon going into the reaction, you better have 3 atoms of carbon coming out, even if they're in a different compound. That's allowed. It's basically what a chemical reaction is that you take the atoms that go in and you rearrange them, and they come out in different combinations. but it's still the same number of atoms of the same elements. They're just connected to each other differently. And just a quick, obvious, fairly obvious example. If you were to form water from hydrogen and oxygen, hydrogen and oxygen are both diatomic gases. So in other words, the atoms only come in pairs. So hydrogen would take the form of H2 and oxygen would take the form of O2. And we try to form H2O from that. And looking at what specifically is going on here, though, you've got two hydrogen atoms going in, these two, and you've got two hydrogen atoms coming out. So that is okay with the law of the law of conservation of matter. But you've got two oxygen atoms going in, and you've only got one coming out. That is not okay with the law of conservation of matter. Where did that other oxygen atom go? It can't just disappear into nothing. It has to go somewhere. To draw this out sort of graphically to illustrate what I'm talking about, H2 is, you can represent like this. And O2 you can represent like this. Why it's a double line between them, don't worry about that now. I just didn't want to draw it wrong. And it comes out as H2O. And again, why the molecule is bent like that, don't worry about it now. I just didn't want to draw it wrong. So you've got obviously two hydrogen atoms going in and two hydrogen atoms coming out. We had two oxygen atoms going in, but only this one coming out. So that is a problem. We can balance the reaction pretty easily just by saying, well, maybe we produce, or maybe we use two hydrogen molecules and we produce two molecules of H2O. In that case, we have a total of 4 hydrogen atoms going in. That is 2 H2s, 1, 2, 3, 4. And we have 4 hydrogen atoms coming out, 1, 2, 3, 4, for the 2 H2Os. For the oxygens, we have 2 oxygen atoms going in the O2, and now we have 2 oxygen atoms coming out, 1, 2, because there are 2 H2Os. And the coefficient, when you write it before a chemical formula, the coefficient, that's this big number in front of the chemical formula, applies to everything within the chemical formula. So that 2 applies not only to the hydrogens, it applies to the oxygen also. So that means 2 oxygen atoms, and I've drawn it out over here. So obviously that's 2 oxygen atoms. And so this version of the equation does obey the law of conservation of matter. So this is what we would refer to as the balanced chemical equation. This reaction up here, that doesn't happen. This reaction does happen. And if all you need to do is put hydrogen and oxygen together in the same container and then light a match or make a spark or something, and boom, you've got water, just like that. And it literally would be boom too, because hydrogen is pretty explosive, especially in the presence of oxygen. Okay, so for writing and balancing chemical equations, we need to remember that the molecular formula gives the content of each molecule or formula unit of the compound. Molecule technically would refer only to covalently bonded compounds, while formula unit would refer to the formula for an ionic compound. But we often use the word molecule to refer to both of those. So, referring to NaCl as a molecule of salt, technically that's wrong, but it's close enough to reality that we can let it slide for now. You can represent the chemical reaction with an equation. Well, we've already done that, so you probably have a pretty good idea of how that works. But anyway, with a chemical equation, you're representing something that has happened, or something that could happen, or something that will happen. And you can think of a chemical equation as being sort of like a symbolic version of a sentence. And you read them like sentences. You read them left to right. You start out with the reactants on the left. You proceed through the arrow, which represents the reaction itself, and you end up with the products on the right. Okay, so reactants go to products. The arrow can be read as the reactants produce the products, or the reactants yield the products, or the reactants go to the products, something like that. Okay, so that's the reaction itself. And then for the reaction above, it's just actually what I already showed with everything drawn out, how everything balances out. We can do this with a slightly more complicated reaction where we say burn propane. When you burn propane, you're burning, and actually, why don't I show, actually, I'm going to show stuff like that step by step in a little while. So I'm going to leave it balanced for now. When you burn propane, each propane molecule has the formula C3H8. And it's actually a chain of 3 carbon atoms with hydrogens all around them. You don't really need to know that now. So, if you need to know it, I'll tell you. And we'll learn how to figure that out later. And for each molecule of propane, it requires 5 molecules of oxygen. And you end up getting out 3 molecules of CO2 and 4 molecules of water. And you can tell that this works out by looking at how many atoms of each element are going in versus coming out. So going in, we've got 1, 2, 3 carbons. And coming out, we've got 1, 2, 3 carbons. C3H8 means 3 carbons in that one molecule. 3 CO2s means 3 molecules, each of which have 1 carbon. So that's 3 carbons. Hydrogen, we've got 8 hydrogens in this one molecule here. And so that's 8 hydrogens in. Coming out, we've got 4 H2Os. That's 4 molecules with 2 hydrogens each for a total of 4 times 2, or 8 hydrogen atoms coming out. So that's balanced also. And then for the oxygens, we have 5 O2s, which should be 5 times 2, or 10 oxygens going in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Coming out, the oxygens are spread around, but we should still have 10. We've got 3 times 2, or 6 for the carbon dioxides, and 4 times 1, or 4 for the H2Os. 6 and 4 is 10. Or you can count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the oxygens balance too. So that version of the equation is the balanced equation for the combustion of propane. And that's the equation because it obeys the law of conservation of matter. Okay, I'm going to stop there, actually. And because we're a little over the time limit, and I'll come back with the next segment in a moment.